In this video, we're going to tie together several things which we've discussed, mainly quotient groups and homomorphisms. So just start with a reminder about quotient groups. So the quotient group of G determined by H is denoted G over H, and it's the set consisting of all the right cosets of H in G. So a quick example. If G is U13 times sub 13, and H is the subgroup generated by 3, which consists of the positive integers 1, 3, and 9, then the elements of the quotient group U13 over the subgroup generated by 3 are the right cosets of H. See, there is the right coset determined by 1, 1, 3, and 9. We'll call that U1. There's the right coset determined by 2. So this we get by multiplying each element of H by 2 in U13, 2, 6, 5. We will call that U2. H times 4. The right coset determined by 4, 4, 12, and 10, which we will call U3, and H7, 7, 8, and 11, which we'll call U4. Okay, so this is a complete list of the right cosets. The right coset determined by 12, for example, is the same as the right coset determined by 4 because 12 is an element of the right coset determined by 4. So we have a complete listing of the cosets, and here is the multiplication table. So remember, for example, to multiply two cosets, let's say U2 times U3. U2 is the right coset determined by 2. U3 is the right coset determined by 4. So U2 times U3 will be the right coset determined by 2 times 4. That is the right coset determined by 8. And the right coset determined by 8, since 8 lies in U4, is U4. So if you look at the table, we see that this entry in the table, in the row headed U2 and the column headed U3, is U4. Okay, so now just a reminder about the really most important fact regarding isomorphisms. So if G star is a group, and we know there is an isomorphism from G star to some other group, assuming we know that, can we say anything about the other group? Yes, we really know exactly what the other group is. The other group is identical to G star as far as the group properties go. We could ask the same kind of thing about homomorphisms. So if there is a homomorphism F from a group G star to another group, can we say anything about the other group? Dealing with homomorphisms now instead of isomorphisms. Here again, the answer is yes. If you know the kernel of the homomorphism, then you can construct a copy of the other group. So if you know the kernel of the homomorphism, then you really know everything there is to know about the other group. The other group will be isomorphic to the quotient group, G over the kernel of F. Okay, so to take an example, sort of an example, If we knew that there were a homomorphism from the group U13 onto some other group, and if we knew that the kernel of the homomorphism was 139, then we would know that the other group has to be isomorphic to U13, the quotient group U13, over the subgroup 139, the subgroup generated by 3. This is the quotient group that we looked at a few slides earlier. So remember, it had 4 elements. U1 was the right coset determined by 1. U2, the right coset determined by 2. U3 was the right coset determined by 4, and so on. So the other group has to be isomorphic to this quotient group, which means it has 4 elements, because the quotient group has 4 elements, and its table has to be identical to the table for U13 over the subgroup generated by 3. Here's the table that we had on a previous slide. So, knowing just the kernel of the homomorphism tells us exactly what the other group looks like. Okay, this is an example of what's called the fundamental homomorphism theorem. Okay, the theorem says that what happened in our example always happens. Assume that the function f from g into j is a homomorphism from the group g star onto the group j circle times. Let h be the kernel of f. Then h is a normal subgroup of g. And the quotient group, g over h, is isomorphic to the group j. Here's a very bare bones outline of the proof. So we would be assuming that we had a homomorphism f from g on to j. Okay, the theorem says that h is a normal subgroup of g. That part I'm leaving for the exercises. The other part of the theorem is that the quotient group g over h is isomorphic to j. So to prove this part, we need to find a function that takes right cosets of g and gives us elements of j as output. We will call that function psi. Okay, so we're assuming f is a homomorphism from g onto j. So f takes elements of g as inputs and gives us elements of j as outputs. Okay, so now we're going to define the function psi from the quotient group into j. So psi takes as an input a right coset of h and gives us as an output an element of g. So given a right coset, h times x, what is psi of that right coset? Well, there's sort of a natural choice. Psi of the right coset will be f of x. Right? F takes inputs from g and gives us outputs in j. Okay, several things we have to prove about psi. The first is that this definition doesn't depend on how we represent the right coset. So we would have to argue that if we had 2 different representations, h times x and h times y of the same coset, then this definition of psi gives us the same output. We would have to verify that the homomorphism equation holds, so we have to know that psi preserves the operations. And we would have to argue that psi is 1-to-1 and on to j. So that would mean that psi fulfills the requirements for being an isomorphism. So part of that proof will be in the exercises. Okay, so let's take an example. Here is a homomorphism from U9 to U3. We're not going to prove it. We've shown that functions like this are homomorphisms in the past. So f of x equals x mod 3 will define a homomorphism from U9 to U3. And as usual, we're using times sub 9 in U9 and times sub 3 in U3. Okay, the kernel of f is easy to find. 1, 4, and 7. Right, these are the elements of U9 that give you 1 when you plug them into the function f. So f of 4, for example, is 4 mod 3, which is 1. F of 7 is 7 mod 3, which is 1. Okay, and the quotient group consists of the right cosets of the kernel. So there is the right coset h times 1, and there is the right coset h times 2. Two right cosets. By the theorem, there is an isomorphism from an isomorphism psi from the quotient group to U3. And the proof of the theorem tells us what it is. It tells us how to find psi of the first coset and how to find psi of the second coset. Psi of the coset 147 is f of 1 equals f of 4 equals f of 7 equals 1. And psi of the second coset is f of any of the 3 of its elements. So for example, psi of 285 is f of 8, which is 8 mod 3, which is 2. Okay, one more theorem that says that every normal subgroup of a group is the kernel of some homomorphism. So we know the kernel of a homomorphism is normal. This is sort of a converse. Every normal subgroup is a kernel. The other group will be the quotient group, G over H. So here's the theorem. If H is a normal subgroup of G star, and then the function from G into the quotient group G over H, defined by f of x equals the right coset determined by x, is a homomorphism, and the kernel of f is H. Let's try an example. So at the beginning of the slides, we looked at U13 times sub 13 and the subgroup generated by 3. Guess we've looked at that group and subgroup twice. G over H consisted of the 4 cosets of H and G. Right, this was H times 1, this was H times 2, H times 4, and H times 7. We called them U1, U2, U3, and U4. So there's the quotient group. And according to the theorem, there is a function f from G to the quotient group for which H is the kernel. And here's how f is defined. F of 1, f of 3, and f of 9 are all equal. They're all equal to the coset 1, 3, 9. So basically, each element of G is being sent to the coset in which it lies. Similarly, f of 2, f of 6, and f of 5 are all equal to the right coset 2, 6, 5. F of 4, f of 12, and f of 10 are all equal to the coset 4, 12, 10. And finally, f of 7, f of 8, and f of 11 are all equal to the right coset 7, 8, and this 1 should be an 11. So this is a homomorphism, and H is the kernel according to the theorem.